this is Dr. Mad. In this series of videos, we're going to explain some of the mysteries of quantum physics and relativity. Yeah, I know, yet another series of videos, on quantum physics, relativity, blah, blah, blah. Yeah, there are hundreds of them, okay? So why yet another one? Well, in this one, we're going to try to explain things, instead of telling you, well, that's the way it works. No. We're going to explain, try to find logical reasons and a logical line of thoughts in order to understand really what is going on. And for that, we need a good model to explain physics, and we're going to build it together. So much fun. Okay, so how are we going to do that? Well, I have to talk to you about the three-world story. Well, the first world, is a physical world that I'm sure you're pretty aware about. It's the world where you find objects like this, the space, with the height and width and depth, no big deal, okay? So we know what we're talking about here, right? Yeah. And then there's a reality world, which is actually what really happens. Unfortunately, we'll never have access to that world. So why bother, yeah, right? Because everything that happens there, we can only have access to it through the physical world. So really what we want to focus on is to explain how the physical world works, as opposed to try to define some theory that we cannot, verify because we don't have access to the reality world, the world of the Matrix, or of God, of the master of puppets. It's crazy. Anyway, so these are the first two worlds I wanted to talk about. But again, the first one, reality world, forget about it. Let's focus on this one. And in order to find a model for this one, well, we need the third world, which is the mathematical world. And what's interesting is that for a good model to work, we have to find a match, correspondence between every object in the physical world to an object in the mathematical world. For instance, here we have a ball, this red sphere here, and we can assign to that object an object in the mathematical world, and in this case, just an equation like that. And that's quite interesting because for each object, the physical world, we must have one object in the mathematical world. And what's also interesting is that if we change some of the properties here of the object, well, the properties must change also in the mathematical world. Okay? And what's even more interesting is once you have defined, math object here, which corresponds to a physical object here, you can also apply functions to it, actions or operations, if you wish, to that object. And then there is something equivalent happening here in the physical world, okay? And again, for each action like this, there should be a function here in the mathematical world. And this correspondence, between each and every object and each and every action has a name. It's called an isomorphism. So a good model should be an isomorphism between math and physical worlds, okay? Now, because we only have access to the physical world, forget about the reality world, we need to find a mathematical model for that physical world. Not for the reality world. And that will allow us to verify that our math model works by measuring elements of an object state. Okay? We'll define what a state means here. Now, what should a good model look like? Because, we've seen what a model could look like, but what do we need to build that model? Well, the first thing we just saw, we need an isomorphism. Okay, fine. Now, the next thing is we want to minimize the number of independent assumptions, postulates or whatever you call them. In other words, we want to build something from a minimum number of hypotheses, again, assumptions. Because it would be too easy. Every time there's something new, you say, oh, okay, well, I'll create, something in my mathematical world just for that, and, you cannot derive much things there. What you want is a minimum number of assumptions, and then from those assumptions, derive in a logical way, all other things happening in the math world, and therefore in the physical world, since they are isomorphic. So that's fantastic. And of course, the mathematical world should allow to predict things that have not been measured yet in the physical world. That's how progress is made. You calculate things with your paper and pencil or with a big computer, and then you find results and you say, oh, yeah, that's interesting, because if my model is good, then that means this should happen also in the physical world. That's how you make inventions, Yeah, fascinating. And also, of course, on the other way, it implies that if you find something new in the physical world, well, you better be sure that it also happens in your mathematical world. Otherwise, your model is not isomorphic. Okay? So, what's the problem then? Well, the problem is that today, most physicists, they really want to tell you how things work. In other words, if they do calculation, they find some results, and they will say, well, if you do the same thing in the physical world, you will get the same results that we calculated in our mathematical world, and this is fine. I mean, it's a good way to do things in the short term, but in the long term, that also means there are holes, in the derivations from the fundamental assumptions that you took, because sometimes what we do in quantum physics, for instance. We say, okay, well, in order for this to work, we have to assume this and this and this. And so these are new assumptions, but they're not derived from existing assumptions. And to me, that's a problem, And that creates some paradoxes, things that don't seem very natural, and for instance, where light is made sometimes of particles, sometimes of waves, actually both at the same time, what does that mean? Where's the logic here? Schrodinger's cat is both dead and alive, at the same time. Come on, superposition of states. What does that mean? Okay, so, well, you can see all the list here, and there's more that we'll look at in this series of videos, and we'll try to give a logical explanation to all these questions that we might have when we look at this list, Okay, so fascinating. So what should we do, to build this good model for physical world? Well, first, probably the most important thing is we need to redefine obvious concepts, such as time. What is time? It seems very natural and easy to answer, but actually it's not that easy. And Einstein showed us why, and space too. When you talk about velocity or speed, it's actually space over time, but you need to define space and time in order to understand what these concepts mean. Measurements is a very key concept in physics, and I'll talk a lot about measurements in these videos, because it's really one of the most fundamental things that we need to look at. It will actually allow us to define things, in the physical world, which is why we don't have access to the reality world. But because we have access to the physical world, measurements become the key concept in order to define what we talk about. Existence. The particle is here or will be there. It will exist or will not exist. What does that mean? We have to define that very precisely. Okay, so reality, we don't care, actually. Because the reality world we don't have access to, so there's nothing we can prove. We can say many things about it, but, we'll never be able to prove it. However, we can measure things in the physical world, and that's why, the physical world is what we should focus on. Now, in addition to that, in order to define this, we'll also have to explain why we use certain tools, because people tell you, particle state, is a Hilbert space vector, and we use Hermitian operators, to get the values, etc., etc. But why? We have to explain that, and that's actually pretty easy to do, but we have to define things very carefully. So, why we use complex numbers, Hilbert spaces, Hermitian operators, tensors. Tensors are very powerful mathematical objects, and we will see why we use them, in particular in general relativity, but also in a lot of other parts of physics. That's so fascinating. So that's what we're going to do in the coming videos. So stay tuned.